All right, here are the notes for concepts of limits. It's introductory, one of the first topics you deal with in calculus. I'm going to talk about limits here. Thin this out. All right, sometimes a limit can be approached and not be reached. Sometimes a limit can be reached. So what is a limit? So if f of x becomes arbitrarily close to a unique number, so as the y coordinate gets closer and closer to a specific number L, as x approaches a number C from both the left and the right, then the limit of f of x as x approaches C is L. Okay, kind of a lot going on there. We see a minus there, that means you're coming in from the left. If you see the little plus sign there, that means you're coming in further from the right. So as x gets closer and closer and closer to some value C, the y coordinate gets closer to some value L. So it's approaching it. We'll see what that means numerically. Let's look at a table to kind of make sense of it. Algebraically, just plug in and hopefully you get a value that's not indeterminate. Graphically, you can tell as well. And there's many features and characteristics, properties, and whatnot that will apply to these limits as well. Okay, so let's look at some examples. I'm going to use these notes that are already filled out because the tables are already created. Okay, so the limit as x approaches 2 of 3x minus 2. All right, let's start with numerically. Let's just check out this table here. So as x gets closer and closer to 2, all right, as x gets closer to 2, so here's 2. So we're going to plug in x coordinates that are to the left of the number 2, right? So there's 2, there's 1.99, and so forth, and then to the right, 2.01, and so forth. So let's plug in. Excuse me, I have allergies. So as you plug in 1.9 into our function here, you get a y coordinate of 3.7. Get closer to 2, plug in 1.99, you get 3.97. So from the left, as you plug in the number, your y coordinate will get closer and closer to 4. In this case, you can actually plug it in. Plug in 2 and you will get exactly 4, which we'll see here in a second. From the right side, so from the right side of the number 2, so 2.01, 2.1, the y coordinates also approach 4. So as x approaches 2 from both directions, left and right, the y coordinate approaches 4. So numerically, we can see from the table. Algebraically, you just plug it on in. So plug it in, it equals 4. If you can plug it in and you get an answer, you're done. If you get an indeterminate form, something like 0 over 0, there'll be other methods that we will use to determine it algebraically. Graphically, so if you graph it, as x approaches 2, the y coordinate approaches 4 from the left and the right. So as you plug in x's going towards 2, the y coordinate gets closer to 4. Graphically, we're approaching this point right here. From the other side, from the right, as x gets closer to 2, the y coordinate also gets closer to 4, approaching this specific point. So again, minus, so we come in from the left. So we're going this way. The function gets closer and closer to 4 for the y coordinate. If we come in from the right, same thing will occur. So as we approach 2 from both sides, the y coordinate approaches the same value, in which case we can state the limit as x approaches 2 We don't need any signs because on the left and the right you get the same result. So the limit as x approaches 2 of 3x minus 2 is equal to 4. The limit is equal to 4. There's number 1. Number 2, what's the limit as x approaches 1? So let's do it numerically. So as we plug in x values from the left of 1, so there's 1. So to the left, so smaller than it, 0.99, 0.90, 0.5. It appears the y values are approaching 2. On the right side of 1, so number is greater than 1, 1.01, 1.1. Seems that the y values are getting smaller and also approaching 2. So it appears the limit is 2, but we'll have to do some verifying or plug in much more values to determine for sure. Algebraically, what happens? All right, we plug in 1, you're going to get 0 divided by 0. That's an indeterminate form. You will hear that word quite a bit. We cannot determine the limit from that. If you can factor and potentially cancel, which I'll do in a second, you could determine the limit. All right, graphically. So as we plug in x's closer and closer to 1, the y coordinates start approaching this point right here. As you plug in x's on the other side, same thing results. When you plug in 1, though, it is actually undefined. So graphically, there's a hole in the graph right there. There'll be a gap right there. However, we can discuss the limits. As we come in from the left, the y coordinate gets closer and closer to 2, as you can see right here. 1.8, 1.98, plug in closer numbers to 1, and you'll see the y coordinate getting closer to 2 as well. As you come in from the right, the same thing occurs. 3.25, 2.21, 2.020, and so on and so on. So the limits agree from the left and the right. Therefore, the limit as x approaches 1 of our function f of x is 2. Algebraically, let's go ahead and do this one. You'll see more of this later in the next section or two. But let me just go through this, show you real quick. If you can factor this out in a way that cancels this x minus 1, which is causing that discontinuity, because you're dividing by 0 there, do so. So for this one, I factor out x squared, so I'm factoring out my numerator. I'm going to factor out 1. It looks like that. So that is that. Let's go a little further. Erase, erase, erase. All right. So I factored by grouping. So my numerator is x minus 1, x squared plus 1. My denominator is x minus 1. These cancel. So what we have determined is the function that's given, this guy, is the same thing as this one everywhere except when x is 1. So we did a table for that one. So let's go ahead and do a quick table. X squared plus 1. It'll be the same everywhere except when you plug in 1, you'll get 2 for a y coordinate. That's the only difference. Every other x, it would be the same. Graphically, everywhere it's exactly the same, except if you were to graph this guy, this would be closed. You wouldn't have that hole there because it's defined everywhere. But keep in mind, we're not doing that one. We're taking the limit of this function here. They have the same limit, but one is not defined at a certain point. But the limit is 2. So that's one way of determining it, which we'll do more practice on those in subsequent lessons as far as solving it algebraically. All right, long story short, limit is 2. Let's go to number 3. All right, number 3. What's the limit as x approaches 0? All right, if you made a table, kind of see what's happening with the values. So as x gets closer and closer to 0 from the left and from the right, the y coordinates appear to be approaching 2. However, it is undefined there. Because if you plug in 0, you get this 0 over 0, which is an indeterminate form, does not tell you anything. But it appears the limit is 2 as the y coordinate is approaching that. So algebraically, nothing's happening there. There's a method. You can multiply by the conjugate and go from there. Graphically, here it is. So as you plug in x's that are closer and closer to 0, the y coordinates are getting closer and closer to 2. So from the left, the y coordinate approaches 2. From the right, the y coordinate also approaches 2. The equal sign is in the middle. Therefore, the limit itself is 2. The limit as x approaches 0, come on, of f of x, which is defined above, is 2. That's done there. To determine it algebraically, I have a little bit of time on this video, so let's go ahead and go do that. One method would be to multiply it by the conjugate of that denominator, so it has a radical. Whatever be down bottom, do on top. So up top, we're gonna get x times rid of x plus 1, my denominator, x plus 1 minus 1, which is just gonna be x, and then that will cancel. So actually, it's gonna result into square root of x plus 1 plus 1. So what happened here? This function is the same as this function everywhere except when x is 1. When we plugged in 1 over here, we plug in 1, it's undefined, it's indeterminate, undefined. However, if you plug in 1 into this guy, so plug in 1, so 1 plus 1. Here's, give me 1 second, something's not checking out. It should be resulting in 2. Okay, my mistake. X is approaching 0, not 1. So, if we plug in 0 right there, we get the square root of 1 plus 1, which is 2. So if we made a table for this one, when you plug in 1, you get 2. If you were to graph it, it would be closed at this point. But again, we're not doing that function, we're doing this function here, which is not defined there, so it's open. However, it's the same limit. So the limit is 2. So algebraically, if you have something with a radical, consider multiplying by the conjugate to hopefully cancel things out. In particular, cancel things in your denominator that are causing it to be undefined. So that's number 3. That'll be it for this video. The next video will be 4, 5, and 6, the next page of the notes.